Good evening, everyone. Today I am here to present a research paper on characterizing private a large-scale empire of enterprise clustering. Here are my teammates Avantika, Prem, and myself Bharat.
Hi everyone.
Hi everyone.
Mainly, we are selecting for this topic is the reason this paper study analyzes that a large number of Nutanix developments across various companies to understand the pros and cons of the private cloud environments for enterprise. Moving on to the next slide. Yeah, private clouds. Private clouds mainly tells us there has a deployment for requires careful planning for future resource, needs to handle peak demands and hardware failures. Mainly here in private clouds, there are hardware failure rates and more predictable load demands, analytical models for durability and cluster growth prediction. Here there is an image regarding the private cloud. Here we are having a company and its own separate private cloud. Mainly, it is an illustration where private cloud has efficient utilization and saving compared to the traditional IT infrastructures. Coming to here, business in public cloud, businesses are increasing and using the more private clouds for their benefits like security and public clouds with ease scaling like private clouds require more upfront resources provising to avoid issues during the peak usage or hardware failures. This research mainly for first large-scale industry to analyze how the private clouds mainly infrastructure and understand the trade-offs involved. And it also find lower hardware failure rates and more predictable resources and demands. Next, moving on to the challenges in managing enterprising the private clouds. Here, we had identified the key challenges faced by organization and managing their enterprises private cloud. We are highlighting the issues of hardware failures and storage scalability optimization. Mainly, the private clouds has morely increased in improved their security, maximum performance and complete control, cost efficiency, and highly scalable private cloud services. And also, private cloud has limited flexibility in terms of resource scaling since public clouds allow on-demand resources to adjust the capacity based on their needs. But private clouds, on other hand, require careful planning and upfront resource allocations. To avoid this peak usage of hardware failures, we had created the private clouds. And the motivation for our research is here we are having mainly the businesses are increasing gradually and they are using private clouds where the benefits of this private clouds has control infrastructure great security proximity to other enterprise resources. As I mentioned earlier, we had seen a rising private cloud adoption enterprise. This is over a desire have more control than previously where it focused like desktop and public clouds like Azure and AWS, and raising significance of private clouds like security, compliance, and quality of services. The main reason was for using private cloud usage is security and compliance. The research gap for this motivation, mainly the private clouds, is lack of focus on enterprise clusters. And the business drives for this research is security, compliance, and service quality. And the future look was tailored solutions with integration and with existing infrastructure. And private clouds can also offer strong service level agreements compared to the public cloud providers. Coming to the next, Nutanix. Here, this paper analyzes about 2000 clusters from Nutanix private cloud deployments indifferently enterprises. It explores and dependability of hardware and application features in these environments and presents a growth predictive model. In contrast to previous research, it investigates in detail the failure modes of all critical paths in cluster nodes, whereas this study evaluates compute and storage needs. where it measures virtualization related flaws and computes. And it also having hardware failure rates. It also monitors changes in CPU and input and output demands over as a time, as well as changes. Nutanix there is a working set in Nutanix network set and the data sizes. Mainly here we can find out the Nutanix cluster architecture, where the Nutanix cluster architecture is addressing that well-known providers like enterprises, virtual missions, where we are seeing these virtualized execution having package of control virtualized mission, user virtual one, and virtual two, where these can have access legacy file systems, which it is which the cluster manager software performs various tasks and provide their abstraction. Uh, like these virtual missions can cope up with higher expected resource loads and migrate the data across the nodes and both preserve locality to achieve good load balances between between them and respond for both temporary and long-term failures to copying their data leaves nodes in order. And moving on to the table, here we can find a study of the deployments of summary statistics. It has cluster size ranging from 3 to 40 nodes with a total number of 13,394, and it has an per minute clusters is 2,168, and disk population is 70K to 90K. This further highlights that their uniqueness in datasets, where we have many relative small clusters as opposed to prior work with few larger ones. And node configuration. Moving on to this node configuration, mainly it focused on understanding the primary configuration nodes in cluster. It is important to the types of workloads they can run. Here are some figures shown in our table. Like configuration 1 refers to compute heavy nodes like 24 crores, and it consists of 2.5 gigahertz, where as compared to the configuration 3 is more strong heavy around 30 TB of storage, where configuration 2 is an baseline version. And coming to the problem which we addressed in this paper, which is a significant role understanding the failure patterns like input output demands and enterprises the private clouds, particularly mainly on Nutanix deployment. For this, we had found an existing solution like novel analytic model for durability analysis and predictive modeling, whereas they mentioned and not compared to the existing solution. And we had furtherly gave the solutions in next slides where I will show you. And coming to the virtual mission, here in the virtual mission, we had observed a median of 21 virtual missions per node. In this particularly, 3 node clusters are followed by 32 virtual missions. Those 3 nodes have majority in virtual mission, whereas small virtual mission can have one virtual CPU assigned, medium virtual mission that have between 2 and 4 virtual CPU, and large size virtual missions with 5 CPUs. Uh, Moving on to the workloads. Here in workloads, we have collected and sampled Nutanix customers to find out their categories, whereas typically running over the 90% of their clusters. Here in y-axis, we have shown that average virtual CPU per virtual mission, and here on x-axis we can see that uh, size of the cluster nodes. Coming to workloads, we had conducted a survey that which we seen before, but they are the workloads where we can find these are the 4 workloads. First workload is virtual desktop infrastructure, where it practice of hosting a desktop operating system within the virtual machine running the desktop and operating system within a virtual machine running centralized server nodes. With the configuration one is the main reason to observe this category. And server. Server refers like a server workload such as database web servers, where it is having an configuration two. Moving on to the big data. Big data is an also one of the most workload which it is Splunk and Hadoop are the main applications which it is and having a configuration of three. Moving on to other workloads like custom application infrastructure. These are all having and SharePoint and link where it is having and mixed configurations. From next slide, it will be continued by Prem.
Hi everyone. Failure analysis. Analyzing private cloud clusters made from enterprise grade commodity components to understand the failure characteristics. Failure can lead to unpredictability, data loss, and also performance degradation, emphasizes the needs for understanding their nature. Examining failure data across various dimensions such as component return rates and also time to repair. There are two types of failures in private clouds. Hardware failure and and second one is the virtualization failure. Second slide. Next slide. Hardware failure. The distribution of hardware failure in the private cloud will be like this. Hard disk drives accounts for less than 20% of the total hardware failures. Memory issue consists approximately 16% of the hardware failures. And also from the graph, you can see all the like solid state drives, which are SSDs and power supply units, PSUs, are also significant contributions for the hardware failure rates. Understanding annual rate uh, return rates. ARR is a metrics based on actual component replacement report by customers. The ARR provides a realistic picture of hardware failures as experienced in operation environments. The study focuses on enterprise grade hardware, which tends to be more reliable than custom level hardware. The in this the these results can impact how enterprise plan for hardware maintenance and replacement cycles. In this paper suggests that the future research into transit failures, which are automatically handled by software like Nutanix, would be valuable. Exploring the durability and enterprise grade components in depth could more insights into how to further reduce failure rates. The point-wise summary of how structured overview of paper analysis of hardware failures in the private cloud environments. You can see this in the annual return rates graph also. Next slide. Virtualization failures. Virtualization failures are issues that arise from software glitches or incorrect setup with a virtual system. Users incorrectly set up VMware resource pools, leading it to insufficient use of CPUs and memory resources. Problems when users implement migrate network setup, resulting in network issues. In this impact of software bugs, for instance, a bug that causes a key management process in VMware to crash and disrupt the connection between the management and the software. The failures are managed by the teams often have to find temporary workloads such as disabling certain automated process that are triggered these bugs and such kind of things. And for it will in the virtualization it takes time where it depends on the sometimes it may quickly solved and some takes several days. And also it will be prevention by regular training for users on correct configuration procedure, keeping software update to prevent knowledge bugs from causing downtime. And also we can also build planning for resilience by building redundancy into systems to minimize the impact of both hardware and virtualization failures. Next slide. Hardware failures here you can see from the annual return rate around hardware failures are 59.32% as are all hardware failures and virtualization failures are 40.68 failures. Time to repair. Time to repair in for the hardware failures and also for the virtualization failures. Most cloud failures fix themselves without need a person to set up in. This discussion is about the time when someone has manually solved the problems. In the hardware failure, about 25% of hardware failures are need only 1 day or less to fix. Sometimes fixing hardware means waiting for the device or the thing that can sometimes takes time. For virtualization issues like software glitches, half of them are sorted in a day or less. Quick fixes like bug supporting often misconfiguration remotely also. Half of the hardware issues get resolved within 3 days considering to shipping time for parts. Virtualization can be fixed faster because they don't need any physical parts. And hardware issues like those with hard drives and power units are a big part of the problems. Enterprise grade hardware tends to more reliable than the kind of use at home. Virtualization problems are quite common and mostly due to mistakes in how things are set up or bugs in the software. Then this graph it shows the hardware failures and the virtualization failures. Next slide. And when it's come to demonstration of the solution, in the paper, the solution is demonstrated through analytical modeling and empirical data from Nutanix deployment. The demonstration, which focus on theory and real-world data, is repeated across various sections, which lead credence of others' finding. However, including prototype implementation or stimulation could potentially strengthen the demonstration of the solution effectiveness. Workload characteristics. Nutanix cluster measurements provide insight into enterprise workload distinct from customer or transit workloads. Virtualization layer data analysis of virtualization offers valuable information on storage requirements, workset size, and data form in transformation saving specific to the enterprise cluster. Understanding how much storage is used to different workloads helps in resource management of planning. Identifying the active portion of data accessed by applications or user aids in optimizing storage performance. Accessing opportunities for storage efficiency improvement through techniques like duplication and comparison. And SSDs, you can see 80% of the node use less than or equal to 500 GB for the working set. Next slide. Storage requirements and data saving. Storage capacity distribution, about 50% of the nodes have 5 TB or less of storage capacity, which is approximately 70% of nodes have 10 TB or less. This suggests that the storage level monitors applications workloads working set to catch elements in SSDs, reducing access latency. In the data transformation, many clusters perform data transformation like comparison and duplication to cut storage overheads. Analyzing focus on clusters with compression only, which makes about 50% of the sample data. Next slide. In this slide, the image is graphically representation of data transformation saving from cluster running server and VID workloads. Compression is more effective than duplication across both server and VDA workloads, with 60% of server cluster achieving up to 40% of saving in storage space. Duplication alone provides moderate saving with both server and VDA cluster showing up to 40% saving ratio of 97th percentile. The combination of comparison and duplication offers the highest saving and suggestion strategic effect through the primary saving drive in comparison. Utilizing both data reduction strategies can lead to enhanced performance by allowing more data to be stored on faster SSDs, improving application performance and recover capabilities after node failures. And achievements of the objectives in the paper, the author appears to achieve their objectives by providing a comprehensive characterization of enterprise private clouds and proposing models for durability analysis and predictive modeling. The paper contributes to the broader understanding and operational management of private cloud environments. Next slide. Predictability. In this, we can see that looking at the data of storage used for uh, 8 months from many computer systems, Half of the systems checked used only 20% or less of the storage space they had. This means lot of storage space wasn't even used at all. The same group of system had a very little chance in how much storage that can be used over time. This shows their storage doesn't need any downtime. It is very stable. 80% of the system used only half of or less than the available space. This point to a stability and predictability pattern even when using more space. This way, these systems started to use more storage over wasn't in random. It's like followed a pattern. Generally, companies are able to predict how much storage they will need because the use for follows a steady pattern. Next slide. CPU and IO measurements. CPU utilization. On average, 80% of the clusters use 20% or less CPU, indicating the clusters generally have an heavy texture. Even at the 99th percentile, most clusters don't even exit 60% CPU. When it comes to the stability, the patterns in CPU usage are stable over time, suggesting that there wasn't a significant need for scalable computing resource in the enterprise workloads. When it comes to IO monitoring, the number of IOPS is another active metrics with 60% of the node performing 100,000 or fewer IOPS on average and maintaining a standard deviation below 450. IOPS capacity, most nodes manage their IO well at the 95th percentile node perform at mostly 6,000 IOPS, within the node's maximum supported limits and indicated that IO loads are generally manageable across clusters. Next slide. Workload analysis. In this workload analysis, here we can give the in a we can get the workload in the sample cluster were introduced. This section offer a detailed analysis of distinct characteristics serving as an indicator for calculating IOPS requirements, VCPUs, VM sizes, etc. Average number of VPUs per node are in the you can see here. VID workloads such as Citrix and Desktop, VMware Horizon exhibit a higher average number of VM per node, approximately 26 compared to the other workloads, which have around 19. Linux virtual server tends to host relevantly more larger VMs compared to the Windows server, which hosts more smaller VMs. Server workloads like MySQL web server typically run more large VMs compared to a VID like applications. Medium-sized VMs are predominant across all applications. And also on average, there are around 2.5 vCPUs per VM. VID workloads generally have fewer vCPUs per VM compared to the other workloads. These characteristics provide insight into workload distribution and resource utilization pattern, aiding in resource allocation and capacity planning. Next slide. On average, we can see average number of vCPUs per VM. And here VID workloads typically have more VMs per node, resulting in fewer vCPUs and available for VM. And second graph, average number of IOPS per nodes for the different workloads. IOPS is a crucial consideration for VID environments. VMware Horizon or View average 3.5K IOPS per second, while Citrix and Computer average 2.45K IOPS per second. Sorry. Citrix Zen desktops likely use Intellect as a caching proxy to reduce overall I/O loads on the backend. From next slides onward, my friend Avantika will continue. Next slide. Avantika.
Modeling. In the previous sessions, we undertook an extensive characterization of private cloud clusters covering various aspects such as failure rates, compute storage requirements, common workloads, and typical configurations. Building upon these measurements, we will now address key questions relevant to the utilization and management of enterprise clusters. Durability analysis. Durability analysis focus on the session that characterizes the durability of data storage within the private cloud environments. Leveraging the measurements outlined in the earlier sessions, we seek to estimate the probability of successive failures, particularly in the scenarios where the additional node failures before the data from the original failed node can be adequately replicated. Analytical model. To facilitate the durability analysis, we introduced an analytical model that accounts for failure rates and storage requirements. Assuming a failure replication factor of RF24 and random replication across the nodes within the cluster, we derive equations to calculate the time required to create new replicas and probability of new data loss within the defined time intervals. Next slide. Data loss in private clouds. Applying the developed model to real-world scenarios from private cloud clusters involving utilization measurements such as failure rates, IO replication factors, and storage capacity. By quantifying these parameters, we can estimate the probability of data loss over specific time periods. This analysis sheds light on a relationship between replication factors and data durability, offering insights to replication strategies necessary to ensure robust data storage in private cloud environments. As you can see, the data loss graph shown above is a data loss in log scale for different RFs. This illustrates the probability of data loss over a period of 1 year for different replication factors in the private cloud clusters. The graph is represented in logarithmic scale, allowing for clear visualization of data loss probability distribution. X-axis represents the fraction of clusters, while the y-axis denotes the data loss probability. Next slide. Cluster growth analysis. The cluster growth analysis dwells into the understanding of different factors changing cluster size within private cloud environments. Given that the cluster growth is a deliberate aspect of capacity planning in the enterprises, we aim to uncover the underlying drivers behind such growth through a machine learning driven approach. The data driven approach, we frame an analysis as a binary classification problem aiming to predict whether the cluster will increase its size or not. Leveraging a logistic regression model, we prioritize to interpretability over high accuracy, including sparsity over 11 regularizers. Next slide. Data and feature methods. We construct 3 sets of basic features: the cluster size characteristics, storage related information, and performance metrics. These 3 features serve as input for predictive model, enabling us to identify significant predictors for cluster growth. The cluster feature methods construct 3 sets of basic features used for predicting cluster growth. These set of features are based on different aspects of clusters, including general size of characteristics, storage-related information, and performance metrics. These features include N nodes. N nodes denote the feature representative total number of nodes in the cluster. NVMs denotes the number of virtual machines per node in the cluster. RSSD, this represents the SSD usage of to total capacity ratio. RHDD, it represents the HDD usage to HDD capacity ratio, indicating the use of hard disk drive. NVCPS, this feature quantifies the number of virtual central processing units. NIOPS, it represents the number of input-output operations per second. The cluster growth is influenced by several factors, primarily driven by the evolving requirements and demands within the cluster environment. Next slide. Features. As you can see, these are the features that are listed above. These features are useful for cluster growth performance. These features are basically, as they're expanded, they are used for the computational resources power increasing. These often tend to the scaling up of existing clusters or the deployment of new ones to accommodate the growing workload. The cluster growth may also be prompted by organizational growth, mergers, acquisitions, or new projects that require additional computing capacity to support increased business activities. Moreover, as the number of users and applications accessing the cluster grows, there is need for larger infrastructure to maintain performance and ensure effective resource allocation. Next slide. What drives cluster growth? Cluster size, storage needs, computation needs. These are the cluster requirements that is used for cluster growth and higher computational power. Next slide. Next slide. Evaluation. We have evaluated the model using area under curve AUC, assessing the contribution of each feature set in the predictive cluster growth. Storage-related features emerge as best predictors than performance metrics, with memory models performing better, particularly with second-order information. The evaluating a predictive model for cluster growth, we employed the area under curve metric to do its sustainability for binary classification problems with unbalanced data sets. AUC provides a comprehensive measure of model's ability to distinguish between positive and negative instances over various threshold values. We observed that our model has achieved 0.64 AUC, indicating moderate discriminative power. While this performance may not be considered exceptionally high, it is noteworthy given our emphasis on the interoperability rather than maximizing accuracy. We have conducted a separate study to assess the relative importance of different feature sets in predicting cluster growth. Our findings relieved that cluster size characteristics and storage requirements were particularly informative, outperforming the performance metrics. We have analyzed the performance of memory versus performance-less models, with performance models exhibiting superior predictive performance, especially when considering historical data up to previous time spans. These suggest that the incorporating temporal information enhances the model predictive capacity by capturing trends and patterns in cluster growth dynamics over time. Next slide. Next slide. Conclusion. The paper is well organized, methodically laying out research and findings with clarity. Figures and tables are effectively used to illustrate the study results. Improvement could be made with expanded discussion on related work, which could provide a clearer context for the reader. Readers gain an understanding of the unique characteristics and challenges of enterprise private clouds. The paper emphasizes the value of analytical model for managing such environments and proposes significant specific models. In conclusion, our study contributes to a deeper understanding of challenges and trade-offs associated with the use of private clouds in enterprise settings. By bridging the gap between theory and practice, we aim to provide actionable guidance for the design and management of private cloud clusters. Overall, the paper presents a thorough investigation into the characteristics of challenges of enterprise private clouds, offering valuable insights and analytical models to aid their management. The organization of this paper is commendable, providing a clear and systematic presentation of the research and findings. Figures and tables are effectively utilized to elicit the study results, enhancing the clarity and comparability of presented information. However, to improve the paper, it could be beneficial to expand the discussion on related work. Providing a comprehensive review of existing literature would offer the benefit for the reader in the clear of context. Next slide. Thank you.